In the previous examples we've done on shear forces, we've only considered point loads. Now we're going to move on to the situation where we have a uniformly distributed load. We're going to have a constant loading intensity W, and we'll have a simply supported beam of length L, pin support on the left and a roller support on the right. And we're going to do exactly as we've done for the previous examples, and first of all start the problem by calculating the reactions. So to calculate the reactions, remember we need to have a free body diagram of the entire system that we're looking at. So we have our A, Y, where we're calling the left hand edge A, our B, Y for the right hand edge, and what we could do is we'll either use the UDL or we'll create an equivalent force, and that equivalent force needs to act down its centroid, and so the equivalent force is W times L, and that would act at the position the centroid, which is L upon 2. So now we use some of the forces in the Y direction to calculate these reactions. So for equilibrium, we have some of the forces in the Y direction, RAY plus RBY equals W times L pointing downwards. From the symmetry of the problem, or by taking moments, therefore we can calculate that RAY is equal to RBY, which equals WL upon 2. So we have the reactions from the problem. Now, as before with the point load problems, we're going to move on and we're going to use the method of sections on a portion of the beam. We're going to start again from the left hand side of the beam A. So to method of sections, and again we draw the free body diagram that we're considering and put a rough edge on the right hand side to show that that's where we're cut. And let's draw the free body diagram. So we know this reaction now at A is WL upon 2, and in this we also assuming up on the left, down on the right for the positive shear force convention. So we're going to put a V pointing downwards on this right hand side where we've made the cut, and in this case now we're going to put the full UDL, not the equivalent load, upon there, and we have the coordinate system, so we're taking X in the horizontal direction, and again we take the sum of the forces in the Y direction, so sum of the forces in the Y direction for this system. So we have, pointing in an upwards direction, we have WL upon 2. We have the loading on this portion of the section, so we have a loading intensity of W. So we have W times X is the total load, and that's pointing downwards, so we'll give that a negative. And we also have V pointing downwards, so we'll also consider that negative. And to be in equilibrium, that all needs to equal to 0. And we can now rearrange this in terms of V, and we get that V equals WL upon 2 minus WX. Okay, so we have a function of X for the shear force diagram. So, and if we look at this, remembering, so Y equals mx plus c, but this is indeed the equation of a straight line. So we note straight away we have the equation of a straight line. The shear force varies linearly in response to a uniformly distributed load. And the second thing to also note, going all the way back to the original drawing of the system, is this loading doesn't have any abrupt changes. And as a result of there not being any abrupt changes, is that this function is valid for the entire section of the beam. So what we're going to do just quickly is evaluate this function at different parts along the beam. So if we consider along the beam where the coordinate x is less than L upon 2, so up to halfway, then we put in W L upon 2 minus W something less than L upon 2, means that V would be positive in this section of the beam. At x is greater than L upon 2, here we have the converse situation where we have W L upon 2 minus W times something bigger than L upon 2, and therefore V would be negative in this portion of the beam. And we'll even look at the special case that x is actually equal to L upon 2, and we have WL upon 2 minus WL upon 2, so would be equal, so V would be equal to 0 at this point. The shear force is 0. Okay, and we're going to use this bit of data to draw our shear force diagram. So let's draw a coordinate axes. And so we know at the left hand side we could put that we would just have the shear force WL upon 2. And we know at the right hand side we have WL upon 2. At the right hand side as well. And choosing the line tool now. And then we have a linear function varying between the two of them and passing through 0 at the point x equals L upon 2. So again, we'll put a coordinate axis V and the units that you're considering in the system. This is the coordinate x along the beam, and we can mark up some points along the beam. So x equals 0, x equals L upon 2, and x equals L. And this is the shear force diagram for a UDL on a simply supported beam.